Sea level rise. Between 1901 and 2018, the average global sea level rose by 15 to 25 centimeters, 6 to 10 in, or an average of 1 to 2 millimeters per year. This rate accelerated to 4.62 millimeters per year for the decade 2013 to 2022. Climate change due to human activities is the main cause. Between 1993 and 2018, thermal expansion of water accounted for 42% of sea level rise. Melting temperate glaciers accounted for 21%, with Greenland accounting for 15% and Antarctica 8%. Sea level rise lags changes in the Earth's temperature. So sea level rise will continue to accelerate between now and 2050 in response to warming that is already happening. What happens after that will depend on what happens with human greenhouse gas emissions. Sea level rise may slow down between 2050 and 2100 if there are deep cuts in emissions. It could then reach a little over 30 centimeters, 1 foot, from now by 2100. With high emissions it may accelerate. It could rise by 1 m, 31 halves ft, or even 2 m, 61 halves ft, by then. In the long run, sea level rise would amount to 2 to 3 m, 7 to 10 feet, over the next 2,000 years if warming amounts to 1.5 degrees Celsius 2.7 degrees Fahrenheit. It would be 19 to 22 meters, 62 to 72 feet, if warming peaks at 5 degrees Celsius 9.0 degrees Fahrenheit. Rising seas ultimately impact every coastal and island population on Earth. This can be through flooding, higher storm surges, king tides, and tsunamis. These have many knock-on effects. They lead to loss of coastal ecosystems like mangroves. Crop production falls because of salinization of irrigation water, and damage to ports disrupts sea trade. The sea level rise projected by 2050 will expose places currently inhabited by tens of millions of people to annual flooding. Without a sharp reduction in greenhouse gas emissions, this may increase to hundreds of millions in the latter decades of the century. Areas not directly exposed to rising sea levels could be affected by large-scale migrations and economic disruption. At the same time, local factors like tidal range or land subsidence, as well as the varying resilience and adaptive capacity of individual ecosystems, sectors, and countries will greatly affect the severity of impacts. For instance, sea level rise in the United States, particularly along the U.S. East Coast, is already higher than the global average, and is expected to be 2 to 3 times greater than the global average by the end of the century. Yet, of the 20 countries with the greatest exposure to sea level rise, 12 are in Asia. Bangladesh, China, India, Indonesia, Japan, the Philippines, Thailand, and Vietnam collectively account for 70% of the global population exposed to sea level rise and land subsidence. Finally, the greatest near-term impact on human populations will occur in the low-lying Caribbean and Pacific islands. Many of those would be rendered uninhabitable by sea level rise later this century. Societies can adapt to sea level rise in 3 ways: by managed retreat, by accommodating coastal change, or by protecting against sea level rise through hard construction practices like seawalls, or soft approaches such as dune rehabilitation and beach nourishment. Sometimes these adaptation strategies go hand in hand, at other times choices must be made among different strategies. A managed retreat strategy is difficult if an area's population is quickly increasing. This is a particularly acute problem for Africa, where the population of low-lying coastal areas is projected to increase by around 100 million people within the next 40 years. Poorer nations may also struggle to implement the same approaches to adapt to sea level rise as richer states, and sea level rise at some locations may be compounded by other environmental issues, such as subsidence in so-called sinking cities. Coastal ecosystems typically adapt to rising sea levels by moving inland, but may not always be able to do so, due to natural or artificial barriers. Observations. Between 1901 and 2018, the global mean sea level rose by about 20 centimeters, or 8 inches. More precise data gathered from satellite radar measurements found a rise of 7.5 centimeters, 3 in, from 1993 to 2017, average of 2.9 millimeters per year, accelerating to 4.62 millimeters per year for the decade 2013-2022. Regional variations. Sea level rise is not uniform around the globe. Some landmasses are moving up or down as a consequence of subsidence, land sinking or settling, or post-glacial rebound, land rising due to the loss of weight from ice melt. Therefore, local relative sea level rise may be higher or lower than the global average. Gravitational effects of changing ice masses also add to differences in the distribution of seawater around the globe. When a glacier or an ice sheet melts, the loss of mass reduces its gravitational pull. In some places near current and former glaciers and ice sheets, this has caused local water levels to drop, even as the water levels will increase more than average further away from the ice sheet. Consequently, ice loss in Greenland has a different fingerprint on regional sea level than the equivalent loss in Antarctica. On the other hand, the Atlantic is warming at a faster pace than the Pacific. This has consequences for Europe and the US East Coast, which receives a sea level rise 3 to 4 times the global average. The downturn of the Atlantic meridional overturning circulation, AMOC, has been also tied to extreme regional sea level rise on the US northeast coast. Many ports, urban conglomerations, and agricultural regions are built on river deltas, where subsidence of land contributes to a substantially increased relative sea level rise. This is caused by both unsustainable extraction of groundwater and oil and gas, as well as by levees and other flood management practices preventing the accumulation of sediments which otherwise compensates for the natural settling of deltaic soils. Total human-caused subsidence in the Rhine-Neuschel Delta, Netherlands, is estimated at 3 to 4 m, 10 to 13 feet, over 3 meters, 10 feet, in urban areas of the Mississippi River Delta, New Orleans, and over 9 meters, 30 feet, in the Sacramento-San Joaquin River Delta. On the other hand, post-glacial isostatic rebound causes relative sea level fall around the Hudson Bay in Canada and the northern Baltic. Projections. There are two complementary ways of modeling sea level rise and making future projections. In the first approach, scientists use process-based modeling, where all relevant and well-understood physical processes are included in a global physical model. An ice sheet model is used to calculate the contributions of ice sheets, and a general circulation model is used to compute the rising sea temperature and its expansion. While some of the relevant processes may be insufficiently understood, this approach can predict nonlinearities and long delays in the response, which studies of the recent past will miss. In the other approach, scientists employ semi-empirical techniques using historical geological data to determine likely sea level responses to a warming world, in addition to some basic physical modeling. These semi-empirical sea level models rely on statistical techniques, using relationships between observed past contributions to global mean sea level and global mean temperature. This type of modeling was partially motivated by most physical models in previous intergovernmental panel on climate change, IPCC, literature assessments having underestimated the amount of sea level rise compared to observations of the 20th century. Projections for the 21st century. The Intergovernmental Panel on Climate Change provides multiple plausible scenarios of 21st century sea level rise in each report, starting from the IPCC First Assessment Report in 1990. The differences between scenarios are primarily due to the uncertainty about future greenhouse gas emissions, which are subject to hard-to-predict political action, as well as economic developments. The scenarios used in the 2013 to 2014 Fifth Assessment Report, AR5, were called Representative Concentration Pathways, or RCPs. An estimate for sea level rise is given with each RCP, presented as a range with a lower and upper limit, to reflect the unknowns. The RCP 2.6 pathway would see GHG emissions kept low enough to meet the Paris Climate Agreement goal of limiting warming by 2100 to 2 degrees Celsius. Estimated SLR by 2100 for RCP 2.6 was about 44 centimeters. The range given was as 28 to 61 centimeters. For RCP 8.5, the sea level would rise between 52 and 98 centimeters, 201/2 and 381/2 in. The report did not estimate the possibility of global SLR being accelerated by the outright collapse of the marine-based parts of the Antarctic ice sheet, due to the lack of reliable information, only stating with medium confidence that if such a collapse occurred, it would not add more than several tens of centimeters to 21st century sea level rise. Since its publication, multiple papers have questioned this decision and presented higher estimates of SLR after attempting to better incorporate ice sheet processes in Antarctica and Greenland and to compare the current events with the paleoclimate data. For instance, a 2017 study from the University of Melbourne researchers estimated that ice sheet processes would increase AR5 sea level rise estimate for the low emission scenario by about 1/4, but they would add nearly half under the moderate scenario and practically double estimated sea level rise under the high emission scenario. The 2017 Fourth United States National Climate Assessment presented estimates comparable to the IPCC for the low-emission scenarios, yet found that the SLR of up to 2.4 meters 10 feet by 2100 relative to 2000 is physically possible if the high-emission scenario triggers Antarctic ice sheet instability, greatly increasing the 130 centimeters, 5 feet, estimate for the same scenario but without instability. A 2016 study led by Jim Hansen presented a hypothesis of vulnerable ice sheet collapse leading to near-term exponential sea level rise acceleration, with a doubling time of 10, 20, or 40 years, thus leading to multi-meter sea level rise in 50, 100, or 200 years, respectively. However, it remains a minority view amongst the scientific community. For comparison, two expert elicitation papers were published in 2019 and 2020, both looking at low and high emission scenarios. The former combined the projections of 22 ice sheet experts to estimate the median SLR of 30 centimeters, 12 in, by 2050 and 70 centimeters, 271/2 in, by 2100 in the low emission scenario and the median of 34 centimeters, 131/2 in, by 2050 and 110 centimeters, 431/2 in, by 2100 in a high emission scenario. They also estimated a small chance of sea levels exceeding 1 meter by 2100 even in the low emission scenario and of going beyond 2 meters in the high emission scenario, with the latter causing the displacement of 187 million people. The other paper surveyed 106 experts, who had estimated a median of 45 centimeters, 171/2 in, by 2100 for RCP 2.6, with a 5% to 95% range of 21 to 82 centimeters, 81/2 321/2 in. For RCP 8.5, the experts estimated a median of 93 centimeters, 361/2 in, by 2100, with a 5% to 95% range of 45 to 165 centimeters, 171/265 in. By 2020, the observed ice sheet losses in Greenland and Antarctica were found to track the upper end range of the AR5 projections. Consequently, the updated SLR projections in the 2019 IPCC Special Report on the Ocean and Cryosphere in a Changing Climate were somewhat larger than in AR5, and they were far more plausible when compared to an extrapolation of observed sea level rise trends. The main set of sea level rise projections used in IPCC's 6th Assessment Report, AR6, was ultimately only slightly larger than the one in SROC, with SSP 1-2.6 resulting in a 17 to 83% range of 32 to 62 centimeters, 121/20241/2 in, by 2100. SSP 2-4.5 resulting in a 44 to 76 centimeters, 171/2-30 in, range by 2100 and SSP 5-8.5 leading to 65 to 101 centimeters, 251/2-40 in. The report also provided extended projections on both the lower and the upper end, adding SSP 1-1.9 scenario which represents meeting the 1.5 degrees Celsius 2.7 degrees Fahrenheit goal and has the likely range of 28 to 55 centimeters, 11 to 11/2 in, as well as low confidence narrative involving processes like marine ice sheet and marine ice cliff instability under SSP 5-8.5. For that scenario, it cautioned that the sea level rise of over 2 meters 61/2 foot by 2100 cannot be ruled out. And as of 2022, NOAA suggests 50% probability of 0.5 m, 191/2 in, sea level rise by 2100 under 2 degrees Celsius 3.6 degrees Fahrenheit, increasing to greater than 80% to greater than 99% under 3 to 5 degrees Celsius, 5.4 to 9.0 degrees Fahrenheit. Post-2100 sea level rise. Models consistent with paleo records of sea level rise indicate that substantial long-term SLR will continue for centuries even if the temperature stabilizes. After 500 years, sea level rise from thermal expansion alone may have reached only half of its eventual level, which models suggest may lie within ranges of 0.5 to 2 m, 11 61/2 foot. Additionally, tipping points of Greenland and Antarctica ice sheets are expected to play a larger role over such timescales, with very long-term SLR likely to be dominated by ice loss from Antarctica, especially if the warming exceeds 2 degrees Celsius 3.6 degrees Fahrenheit. Continued carbon dioxide emissions from fossil fuel sources could cause additional tens of meters of sea level rise over the next millennia. The available fossil fuel on Earth is enough to ultimately melt the entire Antarctic ice sheet, causing about 58 meters, 190 feet of sea level rise. In the next 2,000 years, the sea level is predicted to rise by 2 to 3 m, 61 10 feet, if the temperature rise peaks at its current 1.5 degrees Celsius 2.7 degrees Fahrenheit, by 2 to 6 m, 61 191/2 feet, if it peaks at 2 degrees Celsius 3.6 degrees Fahrenheit and by 19 to 22 m, 621/2, 72 feet, if it peaks at 5 degrees C, 9.0 degrees Fahrenheit, 6. SPM 28 if temperature rise stops at 2 degrees Celsius 3.6 degrees Fahrenheit or at 5 degrees Celsius 9.0 degrees Fahrenheit, the sea level would still continue to rise for about 10,000 years. In the first case it will reach 8 to 13 m, 264 to 1/2 feet, above pre-industrial level, and in the second 28 to 37 m, 92 12 11/2 feet. As both the models and observational records have improved, a range of studies has attempted to project SLR for the centuries immediately after 2100, which remains largely speculative. For instance, when the April 2019 expert elicitation asked its 22 experts about total sea level rise projections for the years 2200 and 2300 under its high, 5 degrees Celsius warming scenario, it ended up with 90% confidence intervals of -10 centimeters, 4 in, to 740 centimeters, 241/2 feet, and -9 centimeters, 31/2 in, to 970 centimeters, 32 feet, respectively. Negative values represent the extremely low probability of very large increases in the ice sheet surface mass balance due to climate change-induced increase in precipitation. The elicitation of 106 experts led by Stefan Rahmstorf had also included 2,300 for RCP 2.6 and RCP 8.5. The former had the median of 118 centimeters, 461/2 in, a 17% to 83% range of 54 to 215 centimeters, 211/2, 841/2 in, and a 5% to 95% range of 24 to 311 centimeters, 91/2, 1221/2 in, while the latter had the median of 329 centimeters, 1291/2 in, a 17% to 83% range of 167 to 561 centimeters, 651/202/21 in, and a 5% to 95% range of 88 to 783 centimeters, 341/230/81/2 in. By 2021, AR6 was also able to provide estimates for year 2150 SLR alongside the 2100 estimates for the first time. According to it, keeping warming at 1.5 degrees Celsius under the SSP 1-1.9 scenario would result in sea level rise in the 17 to 83% range of 37 to 86 centimeters, 141/234 in, SSP 1-2.6 a range of 46 to 99 centimeters, 18 to 39 in, SSP 2-4.5 of 66 to 133 centimeters, 26 of 521/2 in, range by 2100 in SSP 5-8.5 leading to 98 to 188 centimeters, 381/274 in. Moreover, it stated that if the low confidence could result in over 2 meters 61/2 foot by 2100, it would then accelerate further to potentially approach 5 m, 161/2 feet, by 2150. The report provided lower confidence estimates for year 2300 sea level rise under SSP 1-2.6 and SSP 5-8.5 as well. The former had a range between 0.5 m, 11/2 feet, and 3.2 m, 101/2 feet, while the latter ranged from just under 2 m, 61/2 feet, to just under 7 meters, 23 feet. Finally, the version of SSP 5-8.5 involving low confidence processes has a chance of exceeding 15 meters, 49 feet, by then. In 2018, it was estimated that for every 5 years CO2 emissions are allowed to increase before finally peaking, the median 2300 SLR increases by the median of 20 centimeters, 8 in, with a 5% likelihood of 1 m, 31/2 foot, increase due to the same. The same estimate found that if the temperature stabilized below 2 degrees Celsius 3.6 degrees Fahrenheit, 2300 sea level rise would still exceed 1.5 meters, 5 feet, while the early net zero and slowly falling temperatures could limit it to 70 to 120 centimeters, 271/2047 in. Measurements. Sea level changes can be driven by variations in the amount of water in the oceans, by changes in the volume of that water, or by varying land elevation compared to the sea surface. Over a consistent time period, assessments can source contributions to sea level rise and provide early indications of change in trajectory, which helps to inform adaptation plans. The different techniques used to measure changes in sea level do not measure exactly the same level. Tide gauges can only measure relative sea level, while satellites can also measure absolute sea level changes. To get precise measurements for sea level, researchers studying the ice in the oceans on our planet factor in ongoing deformations of the solid Earth, in particular due to landmasses still rising from past ice masses retreating, and also the Earth's gravity and rotation. Satellites. Since the launch of Topex/Poseidon in 1992, an overlapping series of altimetric satellites has been continuously recording the sea level and its changes. Those satellites can measure the hills and valleys in the sea caused by currents and detect trends in their height. To measure the distance to the sea surface, the satellites send a microwave pulse towards Earth and record the time it takes to return after reflecting off the ocean's surface. Microwave radiometers measure and correct the additional delay caused by water vapor in the atmosphere. Combining these data with the precisely known location of the spacecraft determines the sea surface height to within a few centimeters, about 1 inch. Rates of sea level rise for the period 1993 to 2017 have been estimated from satellite altimetry to be 3.0 plus or minus 0.4 millimeters, 1/8 plus or minus 1/64 in, per year. Satellites are useful for measuring regional variations in sea level, such as the substantial rise between 1993 and 2012 in the western tropical Pacific. This sharp rise has been linked to increasing trade winds, which occur when the Pacific Decadal Oscillation, PDO, and the El Niño a Southern Oscillation, ENSO, change from one state to the other. The PDO is a basin-wide climate pattern consisting of two phases, each commonly lasting 10 to 30 years, while the ENSO has a shorter period of 2 to 7 years. Tide gauges. The global network of tide gauges is another important source of sea level observations. Compared to the satellite record, this record has major spatial gaps but covers a much longer period of time. Coverage of tide gauges started primarily in the Northern Hemisphere, with data for the Southern Hemisphere remaining scarce up to the 1970s. The longest-running sea level measurements, ANEP, or Amsterdam Ordnance Datum established in 1675, are recorded in Amsterdam, Netherlands. In Australia, record collection is also quite extensive, including measurements by an amateur meteorologist beginning in 1837 and measurements taken from a sea level benchmark struck on a small cliff on the Isle of the Dead near the Port Arthur convict settlement in 1841. This network was used, in combination with satellite altimeter data, to establish that global mean sea level rose 19.5 centimeters, 7.7 in, between 1870 and 2004 at an average rate of about 1.44 millimeters per year. 1.7 millimeters per year during the 20th century. By 2018, data collected by Australia's Commonwealth Scientific and Industrial Research Organisation, CSIRO, had shown that the global mean sea level was rising by 3.2 millimeters, 1/8 in, per year, at double the average 20th century rate, while the 2023 World Meteorological Organization report found further acceleration to 4.62 millimeters per year over the 2013 to 2022 period. Thus, these observations help to check and verify predictions from climate change simulations. Regional differences are also visible in the tide gauge data. Some are caused by the local sea level differences, while others are due to vertical land movements. In Europe, for instance, only some land areas are rising while the others are sinking. Since 1970, most tidal stations have measured higher seas, but sea levels along the northern Baltic Sea have dropped due to post-glacial rebound. Past sea level rise. An understanding of past sea level is an important guide to where current changes in sea level will end up once these processes conclude. In the recent geological past, thermal expansion from increased temperatures and changes in land ice are the dominant reasons of sea level rise. The last time that the Earth was 2 degrees Celsius (3.6 degrees Fahrenheit) warmer than pre-industrial temperatures was 120,000 years ago, when warming due to Milankovitch cycles, changes in the amount of sunlight due to slow changes in the Earth's orbit, caused the Eemian interglacial. Sea levels during that warmer interglacial were at least 5 meters (16 feet) higher than now. The Eemian warming was sustained over a period of thousands of years, and the magnitude of the rise in sea level implies a large contribution from the Antarctic and Greenland ice sheets. According to Royal Netherlands Institute for Sea Research, levels of atmospheric carbon dioxide similar to today's ultimately increased temperature by over 2 to 3 degrees Celsius, 3.6 to 5.4 degrees Fahrenheit, around 3 million years ago. This temperature increase eventually melted 1/3 of Antarctica's ice sheet, causing sea levels to rise 20 meters above the present values. Since the last glacial maximum, about 20,000 years ago, sea level has risen by more than 125 meters, 410 feet, with rates varying from less than 1 millimeter per year during the pre-industrial era to 40+ mm/year when major ice sheets over Canada and Eurasia melted. Meltwater pulses are periods of fast sea level rise caused by the rapid disintegration of these ice sheets. The rate of sea level rise started to slow down about 8,200 years before present. Sea level was almost constant for the last 2,500 years. The recent trend of rising sea level started at the end of the 19th century or at the beginning of the 20th. Causes. The three main reasons warming causes global sea level to rise are the expansion of oceans due to heating, along with water inflow from melting ice sheets and glaciers. Sea level rise since the start of the 20th century has been dominated by retreat of glaciers and expansion of the ocean, but the contributions of the two large ice sheets, Greenland and Antarctica, are expected to increase in the 21st century. The ice sheets store most of the land ice, 99.5%, with a sea level equivalent, SLE, of 7.4 meters, 24 feet 3 inches for Greenland and 58.3 meters, 191 feet 3 inches, for Antarctica. Each year about 8 millimeters, 5/16 in, of precipitation, liquid equivalent, falls on the ice sheets in Antarctica and Greenland, mostly as snow, which accumulates and over time forms glacial ice. Much of this precipitation began as water vapor evaporated from the ocean surface. Some of the snow is blown away by wind or disappears from the ice sheet by melt or by sublimation, directly changing into water vapor. The rest of the snow slowly changes into ice. This ice can flow to the edges of the ice sheet and return to the ocean by melting at the edge or in the form of icebergs. If precipitation, surface processes, and ice loss at the edge balance each other, sea level remains the same. However, scientists have found that ice is being lost, and at an accelerating rate. Ocean heating. The oceans store more than 90% of the extra heat added to Earth's climate system by climate change and act as a buffer against its effects. The amount of heat needed to increase average temperature of the entire world ocean by 0.01 degrees Celsius (0.018 degrees Fahrenheit) would increase atmospheric temperature by approximately 10 degrees C, 18 degrees Fahrenheit. A small change in the mean temperature of the ocean represents a very large change in the total heat content of the climate system. When the ocean gains heat, the water expands and sea level rises. The amount of expansion varies with both water temperature and pressure. For each degree, warmer water and water under great pressure, due to depth, expand more than cooler water and water under less pressure. Consequently, cold Arctic Ocean water will expand less than warm tropical water. Because different climate models present slightly different patterns of ocean heating, their predictions do not agree fully on the contribution of ocean heating to SLR. Heat gets transported into deeper parts of the ocean by winds and currents, and some of it reaches depths of more than 2000 m, 6,600 feet. Antarctic ice loss. The large volume of ice on the Antarctic continent stores around 70% of the world's fresh water. There is constant ice discharge along the periphery, yet also constant accumulation of snow atop the ice sheet. Together, these processes form Antarctic ice sheet mass balance. Warming increases melting at the base of the ice sheet, but it is likely to increase snowfall, helping offset the periphery melt even if greater weight on the surface also accelerates ice flow into the ocean. While snowfall increased over the last 2 centuries, no increase was found in the interior of Antarctica over the last 4 decades. Further, sea ice, particularly in the form of ice shelves, blocks warmer waters around the continent from coming into direct contact with the ice sheet, so any loss of ice shelves substantially increases melt raises and instability. Different satellite methods for measuring ice mass and change are in good agreement, and combining methods leads to more certainty about how the East Antarctic ice sheet, the West Antarctic ice sheet, and the Antarctic Peninsula evolve. A 2018 systematic review study estimated that the average annual ice loss across the entire continent was 43 gigatons, GT, during the period from 1992 to 2002, accelerating to an annual average of 220 GT from 2012 to 2017. The sea level rise due to Antarctica has been estimated to be 0.25 millimeters per year from 1993 to 2005, and 0.42 millimeters per year from 2005 to 2015, although there are significant year-to-year variations. In 2021, limiting global warming to 1.5 degrees Celsius (2.7 degrees Fahrenheit) was projected to reduce all land ice contribution to sea level rise by 2100 from 25 centimeters to 13 centimeters, from 10 to 6 inches, compared to current mitigation pledges, with mountain glaciers responsible for half the sea level rise contribution. And the fate of Antarctica the source of the largest uncertainty. By 2019, several studies have attempted to estimate 2,300 sea level rise caused by ice loss in Antarctica alone. They suggest 16 centimeters, 61 halves in. Median and 37 centimeters, 141/2 in, maximum values under the low emission scenario, but a median of 1.46 meters, 5 feet, meters, with a minimum of 60 centimeters, 2 feet, and a maximum of 2.89 meters, 91 halves foot, under the highest emission scenario. East Antarctica. The world's largest potential source of sea level rise is the East Antarctic Ice Sheet, EIS. It holds enough ice to raise global sea levels by 53.3 m, 174 feet 10 inches. Historically, it was less studied than the West Antarctica as it had been considered relatively stable, an impression that was backed up by satellite observations and modeling of its surface mass balance. However, a 2019 study employed different methodology and concluded that East Antarctica is already losing ice mass overall. All methods agree that the Totten Glacier has lost ice in recent decades in response to ocean warming, and possibly a reduction in local sea ice cover. Totten Glacier is the primary outlet of the Aurora Subglacial Basin, a major ice reservoir in East Antarctica that could rapidly retreat due to hydrological processes. The global sea level potential of 3.5 meters (11 feet 6 inches) flowing through Totten Glacier alone is of similar magnitude to the entire probable contribution of the West Antarctic ice sheet. The other major ice reservoir on East Antarctica that might rapidly retreat is the Wilkes Basin, which is subject to marine ice sheet instability. Ice loss from these outlet glaciers is possibly compensated by accumulation gains in other parts of Antarctica. In 2022, it was estimated that the Wilkes Basin, Aurora Basin, and other nearby subglacial basins are likely to have a collective tipping point around 3 degrees Celsius (5.4 degrees Fahrenheit) of global warming, although it may be as high as 6 degrees Celsius (11 degrees Fahrenheit), or as low as 2 degrees Celsius (3.6 degrees Fahrenheit). Once this tipping point is crossed, the collapse of these subglacial basins could take place as little as 500 or as much as 10,000 years. The median timeline is 2,000 years. On the other hand, the entirety of the EIS would not be committed to collapse until global warming reaches 7.5 degrees Celsius (13.5 degrees Fahrenheit), range between 5 degrees Celsius (9.0 degrees Fahrenheit) and 10 degrees Celsius (18 degrees Fahrenheit), and would take at least 10,000 years to disappear. It is also suggested that the loss of 2/3 of its volume may require at least 6 degrees Celsius (11 degrees Fahrenheit) of warming. West Antarctica. Even though East Antarctica contains the largest potential source of sea level rise, West Antarctica ice sheet, WAIS, is substantially more vulnerable. In contrast to East Antarctica and the Antarctic Peninsula, temperatures on West Antarctica have increased significantly, with a trend between 0.08 degrees Celsius (0.14 degrees Fahrenheit) per decade and 0.96 degrees Celsius (1.73 degrees Fahrenheit) per decade between 1976 and 2012. Consequently, satellite observations recorded a substantial increase in WAIS melting from 1992 to 2017, resulting in 7.6 plus or minus 3.9 millimeters, 19/64 plus or minus 5/32 in, of Antarctica sea level rise, with a disproportionate role played by outflow glaciers in the Amundsen Sea embayment. In 2021, AR6 estimated that while the median increase in sea level rise from the West Antarctic ice sheet melt by 2100 is 11 cm, 5 in, under all emission scenarios, since the increased warming would intensify the water cycle and increase snowfall accumulation over the ice sheet at about the same rate as it would increase ice loss, it can conceivably contribute as much as 41 centimeters, 16 in, by 2100 under the low emission scenario and 57 centimeters, 22 in, under the highest emission one, 7. This is because WAIS is vulnerable to several types of instability whose role remains difficult to model. These include hydrofracturing, meltwater collecting atop the ice sheet pools into fractures and forces them open, increased contact of warm ocean water with ice shelves due to climate change-induced ocean circulation changes, marine ice sheet instability, warm water entering between the seafloor and the base of the ice sheet once it is no longer heavy enough to displace the flow, causing accelerated melting and collapse, and even marine ice cliff instability, ice cliffs with heights greater than 100 meters, 330 feet, collapsing under their own weight once they are no longer buttressed by ice shelves. These processes do not have equal influence and are not all equally likely to happen. For instance, marine ice cliff instability has never been observed and was ruled out by some of the more detailed modeling. The Thwaites and Pine Island glaciers are considered the most prone to ice sheet instability processes. Both glaciers' bedrock topography gets deeper farther inland, exposing them to more warm water intrusion into the grounding zone. Their contribution to global sea levels has already accelerated since the beginning of the 21st century, with the Thwaites Glacier now amounting to 4% of the global sea level rise. At the end of 2021, it was estimated that the Thwaites ice shelf can collapse in 3 to 5 years, which would then make the destabilization of the entire Thwaites Glacier inevitable. The Thwaites Glacier itself will cause a rise of sea level by 65 centimeters, 251/2 in, if it will completely collapse, although this process is estimated to unfold over several centuries. Since most of the bedrock underlying the West Antarctic ice sheet lies well below sea level, it is currently buttressed by Thwaites and Pine Island glaciers, meaning that their loss would likely destabilize the entire ice sheet. This possibility was first proposed back in the 1970s, when a 1978 study predicted that anthropogenic CO2 emissions doubling by 2050 would cause 5 meters (15 feet) of SLR from the rapid waste loss alone. Since then, improved modeling concluded that the ice within waste would raise the sea level by 3.3 m, 10 feet 10 inches. In 2022, the collapse of the entire West Antarctica was estimated to unfold over a period of about 2,000 years, with the absolute minimum of 500 years and a potential maximum of 13,000 years. At the same time, this collapse was considered likely to be triggered at around 1.5 degrees Celsius (2.7 degrees Fahrenheit) of global warming and would become unavoidable at 3 degrees Celsius (5.4 degrees Fahrenheit). At worst, it may have even been triggered already. Subsequent, 2023, research had made that possibility more likely, suggesting that the temperatures in the Amundsen Sea are likely to increase at triple the historical rate even with low or medium atmospheric warming and even faster with high warming. Without unexpected strong negative feedbacks emerging, the collapse of the ice sheet would become inevitable. While it would take a very long time from start to end for the ice sheet to disappear, it has been suggested that the only way to stop it once triggered is by lowering the global temperature to 1 degree Celsius (1.8 degrees Fahrenheit) below the pre-industrial level, i.e. 2 degrees Celsius (3.6 degrees Fahrenheit) below the temperature of 2020-94. Other researchers suggested that a climate engineering intervention aiming to stabilize the ice sheet's glaciers may delay its loss by centuries and give more time to adapt, although it's an uncertain proposal and would necessarily end up as one of the most expensive projects ever attempted by humanity. Greenland ice sheet loss. Most ice on Greenland is part of the Greenland ice sheet, which is 3 kilometers (10,000 feet) at its thickest. Other Greenland ice forms isolated glaciers and ice caps. The sources contributing to sea level rise from Greenland are from ice sheet melting, 70%, and from glacier calving, 30%. Average annual ice loss in Greenland more than doubled in the early 21st century compared to the 20th century, and there was a corresponding increase in SLR contribution from 0.07 millimeters per year between 1992 and 1997 to 0.68 millimeters per year between 2012 and 2017. Total ice loss from the Greenland ice sheet between 1992 and 2018 amounted to 3,902 gigatons (GT) of ice, which is equivalent to the SLR of 10.8 mm. The contribution for the 2012 to 2016 period was equivalent to 37% of sea level rise from land ice sources, excluding thermal expansion. This rate of ice sheet melting is also associated with the higher end of predictions from the past IPCC assessment reports. In 2021, AR6 estimated that under the SSP 1-2.6 emission scenario, which largely fulfills the Paris Agreement goals, Greenland ice sheet melt adds around 6 centimeters, 21 halves in, to global sea level rise by the end of the century, with a plausible maximum of 15 centimeters, 6 in, and even a very small chance of the ice sheet reducing the sea levels by around 2 centimeters, 1 in, due to gaining mass through surface mass balance feedback. The scenario associated with the highest global warming, SSP 5-8.5, would see Greenland add a minimum of 5 centimeters, 2 in, to sea level rise, a likely median of 13 centimeters, 5 in, cm, and a plausible maximum of 23 centimeters, 9 in. Certain parts of the Greenland ice sheet are already known to be committed to unstoppable sea level rise. Greenland's peripheral glaciers and ice caps crossed an irreversible tipping point around 1997, and will continue to melt. A subsequent study had found that the climate of the past 20 years, 2000 to 2019, would already result of the loss of 3.3% volume in this manner in the future, committing the ice sheet to an eventual 27 centimeters, 101/2 in, of SLR, independent of any future temperature change. There is also a global warming threshold beyond which a near-complete melting of the Greenland ice sheet occurs. Earlier research has put this threshold value as low as 1 degree Celsius (1.8 degrees Fahrenheit), and definitely no higher than 4 degrees Celsius (7.2 degrees Fahrenheit) above pre-industrial temperatures. A 2021 analysis of subglacial sediment at the bottom of a 1.4 km Greenland ice core finds that the Greenland ice sheet melted away at least once during the last million years, even though the temperatures have never been higher than 2.5 degrees Celsius 4.5 degrees Fahrenheit greater than today over that period. In 2022, it was estimated that the tipping point of the Greenland ice sheet may have been as low as 0.8 degrees Celsius 1.4 degrees Fahrenheit and is certainly no higher than 3 degrees Celsius 5.4 degrees Fahrenheit. There is a high chance that it will be crossed around 1.5 degrees Celsius 2.7 degrees Fahrenheit. Once crossed, it would take between 1,000 and 15,000 years for the ice sheet to disintegrate entirely, with the most likely estimate of 10,000 years. Mountain glacier loss. There are roughly 200,000 glaciers on Earth, which are spread out across all continents. Less than 1% of glacier ice is in mountain glaciers, compared to 99% in Greenland and Antarctica. However, this small size also makes mountain glaciers more vulnerable to melting than the larger ice sheets. This means they have had a disproportionate contribution to historical sea level rise and are set to contribute a smaller, but still significant fraction of sea level rise in the 21st century. Observational and modeling studies of mass loss from glaciers and ice caps indicate a contribution to sea level rise of 0.2 to 0.4 millimeters per year, averaged over the 20th century. The contribution for the 2012 to 2016 period was nearly as large as that of Greenland, 0.63 millimeters of sea level rise per year. Equivalent to 34% of sea level rise from land ice sources. Glaciers contributed around 40% to sea level rise during the 20th century, with estimates for the 21st century of around 30%. The IPCC Fifth Assessment Report estimated that glaciers contributing 7 to 24 centimeters, 391/2 in, to global sea levels. In 2023, a science paper estimated that at 1.5 degrees Celsius 2.7 degrees Fahrenheit, 1/4 of mountain glacier mass would be lost by 2100 and nearly half would be lost at 4 degrees Celsius 7.2 degrees Fahrenheit, contributing 9 cm, 31/2 in, and 15 cm, 6 in, to sea level rise, respectively. Because glacier mass is disproportionately concentrated in the most resilient glaciers, this would in practice remove between 49% and 83% of glacier formations. It had further estimated that the current likely trajectory of 2.7 degrees Celsius 4.9 degrees Fahrenheit would result in the SLR contribution of 11 cm, 41/2 in, by 2100. Mountain glaciers are even more vulnerable over the longer term. In 2022, another science paper estimated that almost no mountain glaciers can be expected to survive once the warming crosses 2 degrees Celsius 3.6 degrees Fahrenheit, and their complete loss largely inevitable around 3 degrees Celsius 5.4 degrees Fahrenheit. There is even a possibility of complete loss after 2100 at just 1.5 degrees Celsius 2.7 degrees Fahrenheit. This could happen as early as 50 years after the tipping point is crossed, although 200 years is the most likely value, and the maximum is around 1,000 years. Sea ice loss. Sea ice loss contributes very slightly to global sea level rise. If the meltwater from ice floating in the sea was exactly the same as seawater, then, according to Archimedes' principle, no rise would occur. However, melted sea ice contains less dissolved salt than seawater and is therefore less dense, with a slightly greater volume per unit of mass. If all floating ice shelves and icebergs were to melt, sea level would only rise by about 4 centimeters, 11/2 in. Changes to land water storage. Human activity impacts how much water is stored on land. Dams retain large quantities of water, which is stored on land rather than flowing into the sea, even though the total quantity stored will vary somewhat from time to time. On the other hand, humans extract water from lakes, wetlands, and underground reservoirs for food production, which often causes subsidence. Furthermore, the hydrological cycle is influenced by climate change and deforestation, which can lead to further positive and negative contributions to sea level rise. In the 20th century, these processes roughly balanced, but dam building has slowed down and is expected to stay low for the 21st century. Water redistribution caused by irrigation from 1993 to 2010 caused a drift of Earth's rotational pole by 78.48 centimeters, 30.90 in, causing an amount of groundwater depletion equivalent to a global sea level rise of 6.24 millimeters, 0.246 in. Impacts. The impacts of sea level rise include higher and more frequent high tide and storm surge flooding, increased coastal erosion, inhibition of primary production processes, more extensive coastal inundation, along with changes in surface water quality and groundwater. These can lead to a greater loss of property and coastal habitats, loss of life during floods, and loss of cultural resources. Agriculture and aquaculture can also be impacted. There can also be loss of tourism, recreation, and transport-related functions. Coastal flooding impacts are exacerbated by land use changes such as urbanization or deforestation of low-lying coastal zones. Regions that are already vulnerable to the rising sea level also struggle with coastal flooding washing away land and altering the landscape. Because the projected extent of sea level rise by 2050 will be only slightly affected by any changes in emissions, there is confidence that 2050 levels of SLR combined with the 2010 population distribution, i.e. absent the effects of population growth and human migration, would result in 150 million people under the waterline during high tide and 300 million in places which are flooded every year, an increase of 40 and 50 million people relative to 2010 values for the same. By 2100, there would be another 40 million people under the waterline during high tide if sea level rise remains low, and 80 million for a high estimate of the median sea level rise. If ice sheet processes under the highest emission scenario result in sea level rise of well over 1 meter, 31/4 foot, by 2100, with a chance of levels over 2 meters, 61/2 foot, then as many as 520 million additional people would end up under the waterline during high tide and 640 million in places which are flooded every year, when compared to the 2010 population distribution. Over the longer term, coastal areas are particularly vulnerable to rising sea levels, changes in the frequency and intensity of storms, increased precipitation, and rising ocean temperatures. 10% of the world's population live in coastal areas that are less than 10 meters, 33 feet, above sea level. Furthermore, 2/3 of the world's cities with over 5 million people are located in these low-lying coastal areas. In total, approximately 600 million people live directly on the coast around the world. Cities such as Miami, Rio de Janeiro, Osaka, and Shanghai will be especially vulnerable later in the century under the warming of 3 degrees Celsius (5.4 degrees Fahrenheit), which is close to the current trajectory. Altogether, LIDR-based research had established in 2021 that 267 million people worldwide lived on land less than 2 m, 61/2 ft, above sea level, and that with a 1 m, 31/2 ft, sea level rise and zero population growth, that number could increase to 410 million people, 146. Even populations who live further inland may be impacted by a potential disruption of sea trade, and by migrations. In 2023, United Nations Secretary-General Antonio Guterres warned that sea level rises risk causing human migrations on a biblical scale, but sea level rise will inevitably affect ports, but the current research into this subject is limited. Not enough is known about the investments required to protect the ports currently in use, and for how they may be protected before it becomes more reasonable to build new port facilities elsewhere. Moreover, some coastal regions are rich agricultural lands, whose loss to the sea can result in food shortages elsewhere. This is a particularly acute issue for river deltas such as Nile Delta in Egypt and Red River and Mekong deltas in Vietnam, which are disproportionately affected by saltwater intrusion into the soil and irrigation water. Ecosystems. When seawater reaches inland, coastal plants, birds, and freshwater/estuarine fish are threatened with habitat loss due to flooding and soil/water salinization. So-called ghost forests emerge when coastal forest areas become inundated with saltwater to the point no trees can survive. Starting around 2050, some nesting sites in Florida, Cuba, Ecuador, and the island of St. Eustatius for leatherback, loggerhead, hawksbill, green and olive ridley turtles are expected to be flooded, and the proportion would only increase over time. And in 2016, Bramble Cay Islet in the Great Barrier Reef was inundated, flooding the habitat of a rodent named Bramble Cay melames. In 2019, it was officially declared extinct. While some ecosystems can move land inward with the high water mark, many are prevented from migrating due to natural or artificial barriers. This coastal narrowing, sometimes called coastal squeeze when considering human-made barriers, could result in the loss of habitats such as mudflats and tidal marshes. Mangrove ecosystems on the mudflats of tropical coasts nurture high biodiversity, yet they are particularly vulnerable due to mangrove plants' reliance on breathing roots or pneumatophores, which might grow to be half a meter tall. While mangroves can adjust to rising sea levels by migrating inland and building vertically using accumulated sediment and organic matter, they will be submerged if the rate is too rapid, resulting in the loss of an ecosystem. Both mangroves and tidal marshes protect against storm surges, waves, and tsunamis, so their loss makes the effects of sea level rise worse. Human activities, such as dam building, may restrict sediment supplies to wetlands, and thereby prevent natural adaptation processes. The loss of some tidal marshes is unavoidable as a consequence. Likewise, corals, important for bird and fish life, need to grow vertically to remain close to the sea surface in order to get enough energy from sunlight. The corals have so far been able to keep up the vertical growth with the rising seas, but might not be able to do so in the future. Adaptation. Cutting greenhouse gas emissions can slow and stabilize the rate of sea level rise after 2050, greatly reducing its costs and damages, but cannot stop it outright. Thus, climate change adaptation to sea level rise is inevitable. Then the most straightforward approach is to first cease development in vulnerable areas and ultimately move the people and infrastructure away from them. Such retreat from sea level rise often results in the loss of livelihoods, and the displacement of newly impoverished people could burden their new homes and accelerate social tensions. It is possible to avoid or at least delay the retreat from sea level rise with enhanced protections like dams, levees, or improved natural defenses, or through accommodation like building standards updated to reduce damage from floods, addition of stormwater valves to address more frequent and severe flooding at high tide, or cultivating crops more tolerant of saltwater mixing into the soil, even at an increased cost. These options can be further divided into hard and soft adaptation. The former generally involves large-scale changes to human societies and ecological systems, often through the construction of capital-intensive infrastructure. Soft adaptation involves strengthening natural defenses and local community adaptation, usually with simple, modular, and locally owned technology. The two types of adaptation might be complementary or mutually exclusive. Adaptation options often require significant investment, but the costs of doing nothing are far greater. For instance, effective adaptation measures are predicted to reduce future annual costs of flooding in 136 of the world's largest coastal cities from $1 trillion by 2050 if no adaptation was done, to a little over $60 billion annually, while costing $50 billion per year. However, it has been suggested that in the case of very high sea level rise, retreat away from the coast would have a lower impact on the GDP of India and Southeast Asia than attempting to protect every coastline. To be successful, adaptation needs to anticipate sea level rise well ahead of time. As of 2023, the global state of adaptation planning is mixed. A survey of 253 planners from 49 countries found that while 98% are aware of sea level rise projections, 26% have not yet formally integrated them into their policy documents. Only around a third of respondents from Asian and South American countries have done so, compared to 50% in Africa, and greater than 75% in Europe, Australasia, and North America. 56% of all surveyed planners have structured plans which account for 2050 and 2100 sea level rise, but 53% only plan using a single projection, rather than a range of 2 or 3 projections. Just 14% plan using 4 projections, including that of the extreme or high-end sea level rise. Another study found that while greater than 75% of regional sea level rise assessments from the west and northeastern United States included at least 3 estimates, usually RCP 2.6, RCP 4.5 and RCP 8.5, and sometimes included extreme scenarios, 88% of projections from the American South had only a single estimate. Similarly, no assessment from the South went beyond 2,100, while 14 assessments from the West went up to 2,150, and 3 from the Northeast went to 2,200. 56% of all localities were also found to underestimate the upper end of sea level rise relative to IPCC's 6th assessment report,